Okay, Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. This is a lecture which covers the application of stress transformation and application to thin wall pressure vessel and shaft design. So I sort of named this lecture Lecture 3B for the fact that there is a Lecture 3A, which is an example of the application of stress transformation. Lecture 3C covers the test that we have done recently. So this is to complete the lecture on the stress transformation application to thin wall pressure and shaft design. So what is thin wall pressure vessel? A pressure vessel is assumed to be a thin wall pressure vessel when the thickness of the vessel is less than 1/20th of its radius. So for example, if you have a pressure vessel like this, like a pipe, and then you've got thickness and you got the diameter d, so r is equals to d over 2, and if the radius is larger than 20 times the wall, then we can call the pressure vessel to be thin wall pressure vessel. So for example, if your pressure vessel is made from a very thin sheet of metal of, let's say, 0.1 mm, okay, and if it is like a paper, for example, so 20 times 0.1, so we'll have about 2 mm, so that can be considered as a thin wall pressure vessel. If it is made from 1 mm thick, it cannot be, so so the radius has got to be larger than 20 mm. So this is because of the error associated with the assumption when we solve the problem. It is a plane stress kind of problem. There is no stress across the thickness of the pressure vessel. So this is, and they limit the stress or the error to be less than 5%. So it's about managing errors. As we apply the equation to a thicker and thicker wall pressure vessel, the error will grow up to the exact value of the stress in the pressure vessel. So if you look at we'll do two types of pressure vessels, the cylindrical and the spherical, but we'll start with the cylindrical pressure vessel first. So when we have a cylindrical pressure vessel, look at this pressure vessel, simple pressure vessel, and you apply a pressure inside it just like a pipe. So it is continuous along the axis, and then there is a stress. There are two types of stress. Okay, one is called the hoop stress, i.e. the stress along the circumference, and then the other one is called the longitudinal stress. This is along the length of the vessel or along the axis of the vessel. So the hoop stress is along the circumferential direction of the vessel, and the longitudinal stress is along the axis of the pressure vessel. So when you look at the hoop stress, this is how we analyze the conditions of the pressure vessel. So you can see that there is sigma 1 dA is the stress inside the wall of the pressure vessel times the area of the wall. There are two walls, the bottom and the top, and then you've got the pressure vessel, the internal pressure, which is acting and providing the force that is pushing the wall of the vessel out, so PdA. So then we apply the force equilibrium, where the force in the z direction or in the radial direction or the horizontal direction should be 0. So that is equivalent to the hoop stress, sigma 1 here, times 2t, t is the thickness, delta x is the length, minus p 2r delta x. Since delta x is common, we can strike it out, and then we will find that the hoop stress, or sigma theta, equals to sigma 1 equals to p times radius divided by t. We can apply the same technique for the longitudinal stress. The bottom picture here shows the longitudinal stress. So the stress within the wall is providing a resistance force of sigma 2 times 2 pi RT. 2 pi RT is the area of the wall. Okay, So sigma 2 times 2 pi RT minus P, which is the pressure that is acting on the wall. There must be a pressure acting on the wall on the longitudinal side, times P R squared, which is the area inside the pipe, inside the cylinder. So from there you can get the longitudinal stress of sigma x or sigma 2 equals to PR over 2T. So when we compare sigma theta with sigma x, we can say that sigma x is half of sigma theta, PR over T divided by 2. So sigma 1 or sigma in the longitudinal sigma theta equals 2 times the axial stress or the longitudinal stress. So this is what, from this simple force equilibrium, we can identify the stress acting on the system. So if we plot the Morse circle for the Hoops stress and the longitudinal stress, this is what the Morse circle will be. Points A and B corresponds to the Hoops stress and the longitudinal stress. Now the Hoops stress is double of the longitudinal stress, so sigma 2 is twice of sigma 1. And the maximum in-plane shearing stress from this Morse circle is equivalent to the radius, which is the difference between sigma 1 and sigma 2 divided by 2, and that is half of sigma 2, and that is equivalent to 4R over 4T. So the maximum out of plane shearing stress corresponds to 45 degrees rotation of the plane stress element around the longitudinal. So the tau max is equals to PR over 2T. So this is out of plane shearing stress, but this is it's not covered in this section. So the plane stress Morse circle is only A dBE. So you don't have to worry too much about this part of the work, because it's somewhat extra, and the one that we have studied so far only covers the Morse circle that I draw in yellow here. Okay, so the remaining is due to the third component, and third principal stress being 0. This is O, point O, and this is not covered in this course. Just to be so that you are aware of, there is a 3D stress state that we need to consider, but only for the second year we only limit ourselves to the in-plane shearing stress and not the out-of-plane shearing stress as shown in here. So only maximum in-plane shearing stress, which is this point, tau max is equals to half of sigma 2. This is PR over 40. Yeah, this is the tau max that we cover in this distance, tau max in plane. Okay, so that's for cylindrical. Let's move on to the next one. The next one is where we want to cover the stresses in thin wall spherical pressure vessels. There are just two shapes that we have considered now, the cylindrical and the spherical pressure vessels. So the spherical pressure vessels, we also have the hoop stress, but we don't have the longitudinal stress. Even in the longitudinal direction, it's also still considered as hoop stress. So using the static equilibrium, all the forces must be 0. So the forces are coming from the pressure, P pi R square, and this must be resisted by the stress within its half of the spherical pressure vessel. So sigma 2 is the internal stress, and then the area is 2 pi RT. This is an approximation. Yeah. So when you equal this outright, you will find that sigma 1 equals to sigma 2 equals to PR over 2T. So this is sigma 1, and also this is equals to sigma 2. So that's your pressure vessel. So Morse circle for the in-plane transformation reduces to a point where everything is in the same point. A and B are at the same point. Okay, and the tau max in plane is equals to 0. There is no shear stress in this at this point here, and maximum of a plane shearing stress is half of sigma 1. This is out of plane, which we do not cover this area. So basically what we have is a point, reduces to a point. Let me make that is a point, not even a circle. Okay, a point. So that not a circle, because they coincide sigma 1. This happens when sigma 1 equals to sigma 2. Okay, so for that there's only one point there. This is out of plane shear stress. This is out of plane, not covered in our syllabus, second year. Okay, so this is an introduction to you, but what we have here is that your hoop stress and rolling stress is 4R PR over 2T in comparison to the cylindrical pressure vessel, which is 4R over T, PR over T. So the advantage of a thin wall in comparison, if you have a cylinder, for example, we have a cylinder, then it's more advantageous to use that. So now we move on to the application of the stress transformation to shaft design. Okay, so I'm looking at shaft design here. Okay, and look how we apply this to the shaft design. So in the power transmission, we have got three major ways of transmitting the power through the shaft. The first one is with the use of gears. The second one is with the use of chain and sprocket. The third one is with the use of belts and pulleys. There are shafts connecting the belts and the pulleys. So there are shaft here, shaft here. There's always shaft everywhere. On the top part, you can see the shaft very clearly. So if you take away and draw the free body diagram, the forces acting, this is a spur gear, and we assume that there is no axial load acting on it. And we can now reduce the contact between the spur gear teeth to be of F. And then since we know that F is acting at the radius of R from the centroid of the shaft, so we can remove that F and we can transfer all the load to the centroid of the shaft. So it is equivalent to cover with torque equals to FR. And then there is a longitudinal or horizontal force acting normal to the axis of the shaft with that F. And this will cause two things. When you have a force acting normal to the shaft, it will cause a shear force, and also given the distance, it will cause a bending moment. So with that, you have got bending stress. With shear force, it will cause you shear stress if you want to draw the stress element. Coming back to the chain and sprocket here. So the chain and sprocket, I am drawing the free body diagram here, where Ft is the tension of the chain acting on the sprocket. Fs is the tension of the chain acting on the lower sprocket. But the difference between T and S is Ft is the tension on the tension side of the chain, and Fs is the tension on the slack side of the chain. So I put it here, Ft and Fs. Bahagian yang longgar tu tegangannya adalah Fs, bahagian yang tegang itu tension side, tegangannya Ft. And there is an angle here, theta, which I put it there. And similarly for belt and pulley pun kita ada tension side and ada slack side, and also at an angle. But for a chain, the assumption is usually we make that the slack side, the tension is 0. Okay, on the slack side, the tension is 0. But on the pulley, there is you cannot make it 0. So there is a tension on the slack side, and the ratio is about, the tension side is about 3 to 4 times more force than the slack side. This is just for design purposes. So when you try to represent or draw the free body diagram of this shaft, when you are applying a sprocket here, the torque is F cos theta R, if there is an angle here, theta. And then because the slack side is 0, so there is a horizontal force due to the tension from the chain. So Fc cos theta acting at the centroid, and there is also a vertical component from the chain pulling down Ft sin theta. This is all at the tension side. So if theta is 0, then this component is 0. If the chain is fully flat, there is no vertical component. Similarly with the belt, I think the only difference is on the horizontal side, you have to add up the tension and the slack side force, Ft plus Fs, and on the vertical side, you just Ft minus Fs. This is sine theta, this is cos theta. So there's a lot of assumptions here. This is just an introduction so that you know how to apply your stress transformation to the shaft. Okay, so let's move on. As we design of transmission shaft, as I told you, if power is transferred to and from shaft by gears of sprocket wheels, the shaft is subjected to transverse loading. Yeah, this is transverse loading due to forces in mating gears, as well as shear loading due to torque from these forces. So there are the torque and other transverse loading. And transverse loading ada dua direction. One is the vertical one, the others are in the horizontal one. So normal stresses due to transverse loadings may be large, should be included in the definition of maximum shear stress. So tau equals to VQ over IT, you should not omit that. So shearing stress due to transverse are usually small, and their contribution to maximum shear stress may be neglected. So this is normal stress due to transverse load may be large, so that is determination of maximum shear stress. But the shearing stress due to transverse are usually small. This is what we meant by normal stress due to transverse load. This is because when you have we will see some examples here, but usually what this means is that we usually do not consider this component because it's relatively small in comparison where you have a shear stress due to bending. It will now be quite significant. From this we will see how we draw or get that components later on. So so if you design a transmission shaft at any sections, you are subjected to torque. You've got moment about the z-axis, yeah, and you've got moment about the y-axis. Now it's vector representation, yeah. So you've got shear stress acting and also a normal stress acting along the fiber along the shaft. So we have got sigma m equals to mc over I, and then we've got tau m equals to t torque. Cc is the radius, in this C is the radius, and J is the polar moment of inertia. This is a moment of inertia. So where m is the resultant moments. So we have a moment in the y direction, and we have got moment in the z direction. This moment must be perpendicular to each other. Because of the specific shape of a circular shaft, you can find the moments of this. So this is the resulting moment, m square equals to my square plus mz square. So the maximum shear stress, tau max, is equals to the mean value of the stress plus the tau acting on that, and that we can have this mc over 2I plus tc over j square. So for circular cross section, 2I equals to j, and we can then find tau max equal to c over j. We can make this common, and then m square plus t square. So shaft section requirement is j, the polar moment of inertia, divided by c is equivalent to square root of m square plus the torque subjected maximum. Here is maximum, tau max, and then m square. M is the applied, and tau allowable is the allowable shear stress. This is how you check your shafts based on the allowable shear stress. Okay, let's put some notes here so that we can better understand. This is the allowable shear stress. So allowable shear stress. Yeah. Okay, so C is radius, So this is called resulting moment. Resultant moment, if we can ever call it that way, easier for us to remember, due to circular shaft. Yeah, that circular shaft. Okay, anything else that we missed? So this one we are quite clear. I equals to pi d4 over 64, j equals to pi d4 over 32. So 2i equals to 1j. That's what we mean by here. Anything else that we should? So here is the tau max, and then this is the allowable shear stress from the system. So you can use the Morse circle to design the radius, determine the radius suitable given the allowable shear stress. So that's one way of looking at it. Let's move on. So this is an example of a typical system where you've got a motor which is driving a big shaft here, a big gear here, and there is the radius of E is 160, the radius of D is 80, the radius of C is 60, and then these are the takeaway power from other machines. So you put in torque here, it will be lost here, it will lost here, and so 100% will be transmitted. No torque is lost at the bearings. So the shaft rotates at 480 RPM. Which shaft? Transmit 30 kilowatts from motor to gears G and H. Okay, 20 kilowatt is taken here at gear G, 20 kilowatt. So let us write it down here. 20 kilowatts. So here is 20 kilowatt. And 10 kilowatt at gear H. So here is 10 kilowatt. The allowable stress is 50 megapascal. So that's the allowable normal stress, not the shear stress. Find smallest permissible diameter for shaft. Okay, so we need to find the smallest permissible. So we are assuming that we pump in 30 kilowatts here. So here we put 30 kilowatts, and that power goes from this to this gear shaft, and 10 kilowatt goes to this device, and 20 kilowatt goes to that device, and nothing else. So there are certain things that we need to observe. The first one is the direction of the contact. So here the contact is vertical, in the vertical axis, and at E the contact is on the horizontal axis. Yeah, so that is perhaps what we need to know for this moment. So let's see how the solution looks like. So here's what we discussed just now. So we know the equation of P equals to T omega, all right, and then P at E equals to T E omega E, and P at M is equals Tm omega N, and this is all the equation related to this. So at the torque of E equals to P equals to T omega, omega is equals to 2 pi F. So we divide it, and we know that the speed is 8 hertz. Okay, so it's 480 RPM, 8 hertz. So 2 pi 8 hertz equals to, we got the torque here, 597. Okay, and when we have the torque 597, we divide it by the distance, 0.16. This is the distance here, 0.16. Yeah, so let me maybe highlight that with yellow. This is the distance, 1.16, and this is distance 0.16, and that is where we are using it. Okay, similarly we can get 3.73 kilonewton. So that gives us this green answers, which is here. Oh, it's not clear to you. I'm gonna put it so let me just underline it here. 3.73 kilonewton. So you repeat the same analysis for the torque at C, and you will have TC equals to 398 Newton meter, which is here. And then we have got TD 199 Newton meter. I'll put it in a different color. Yeah, so these are the three torques. 3.73 is going in. 597 is here. Let me put this as maybe red. 597 is here. Okay, so you know where your torque and your forces comes from this equation. And you have to find the reactions at bearing B and find the reactions at bearing M. So remember from the previous thing, if we have a bending moment, so we have a bending moment in the horizontal because we have all the forces in the horizontal plane, and we've got one forces in the vertical plane. So we've got moment in the vertical plane, MV, and also we have moment in the horizontal plane. And we can find the resultant of this. So what do we need? How do we find the maximum bending moment? We can draw the moment diagram. So here is a moment diagram, mm squared plus, so we identify critical shaft section from torque and bending moment diagram. Okay, so we need to draw the torque and also the bending moment diagram. So here is for the horizontal, or this is for the vertical one. This is YX. I'm looking at YX here. So we have Y and X. This is the forces from the bearings. So we can do the static equilibrium and find the forces. And this is the bending moment diagram. You can draw the shear forces diagram and the bending moment diagram. Similarly, this is for the horizontal component. You have to find the force equilibrium of the bearing. So here is the bending moment diagram. And plus, there is a torque diagram. The torque that goes in at A, and then 395 absorbed at A, and then at D to E, it is absorbed 597 Newton meters. So we have got the bending moment diagram in the horizontal plane. This is Y. Can I write it here? This is Y, YX plane. Okay, plane. This is in the ZX plane. So ZX plane. And this is a torque diagram. So from here, at the C, at point C, you can see that the bending moment is highest, 1244, and that's 186, and then the torque is 398. So, and we can look at D, for example. At D is 373, and then it's 1160, and then the torque is 597. So they have identified that D is the point that has the highest load. You have to do some calculation before that. You have to find that these numbers are the biggest. So summation of my square plus mz square plus t square is 1160 square plus 373. So it gives you the maximum 1357. So at C it is 1319. At E is 1003. So they have done the calculation for us, luckily. So you can check your calculation at C is 1319, and you can check this at E is 1003. So from there, you identify point D to become the critical cross section because it has the highest number, 1357. Highest. Oh my God, it should be max, yeah. So let's move on. So we now use the formula. That we apply the resultant stress, my square plus mz square plus t square divided by the allowable stress, which is 50 megapascal, equals to J over C equals to 1357 Newton meter equals to 27.14 times 10 to the power minus 6 meter cube. And from there, for solid circular shaft, you can have this formula, pi over 2 c cube equals to g over c, and we can find that the radius is 25.85. This is the radius. So that is the radius. Point C equals to 2002585 mm. This is mm. Yeah. So you specify the closest one, 26 mm. Okay. So, or you find a way to make it into 25 by reducing, or by finding or increasing the allowable. So this is a way of you specifying the minimum allowable shaft diameter. The radius is 25.85. So the diameter is just 2 times the radius. As I said earlier, this is as an introduction to the application of stress transformation in shaft design. It is much complicated topics, but we do not have the time to go into details. But I think if you have followed the lecture, you can see that we started with the stresses, simple stresses, and then we combine the stresses and we use the Mohr circle to find the principal stresses, and the principal stresses we can now relate that to the allowable working stress, allowable shear stress, or allowable maximum stress, and from there we can find its use in the application of designing shaft for power transmission, and also before this for the thin pressure vessel, thin wall pressure vessel. So I hope you have benefited from this. This section, however, will not be covered in the final exam because of the limited time. So this is, as I said, this is an introduction which is useful for you to use in your design course. All right, thank you very much.